All right, we are going to construct a Hermite polynomial where f of x is this function x squared plus 4x minus 5. And we're going to use the data points or the nodes x sub 0 is 2, x sub 1 is -1, and x sub 2 is -6. Now, the Hermite polynomials agree with our function f of x at each of the nodes, and they also agree with the first derivative of our function at each of the nodes. So let's get all of the data that we're going to need to interpolate and match using this polynomial. So first, I'm going to need to know that the function values at each node. So f of x0, I'm going to plug in 2 to my function f here, and that'll give me 7. Okay, and then I'm also going to need to know f evaluated at x1, so I'm going to plug in -1 here, -1 squared plus 4 times -1 minus 5. And then that's going to give me -8. And I'm going to need to know the value at x sub 2. So I will substitute in -6 to my function f of x. And that'll also give me 7. So those are the heights that I need to match, the height of the function. I also need to match the first derivative of this function. So first, let's compute that first derivative. F prime is 2x plus 4. And the Hermite polynomial will agree with the derivative f prime at each of these nodes. So let's compute f prime at x sub 0. That'll be 2 times 2 plus 4, which will be 8. F prime at x1 will be 2 times -1 plus 4, which will give me 2. And f prime at x2, 2 times -6 plus 4 will give me -8. Okay, so really it's these, let me highlight this, it's these 6 pieces of information that my Hermite polynomial is matching. I have 6 pieces of information. And the degree of the polynomial is always one fewer, one less than the number of sort of information items that I'm trying to match. So here I have 6 pieces of information, 3 points, and 3 derivatives. So I'm going to construct H5, a 5th degree polynomial. 5th degree polynomial. And the way I'm going to do that is using a divided difference table. But I'm going to need to do something a little bit different because I have derivative information that I need to include in this table. So when I make my divided difference table, I'm going to need to repeat the values, the nodes in the first column. Let me make this a little bit smaller so that I can fit the whole table on here. See if I can get this all on one line. Okay, move this up just a little bit. All right, so when I construct this table, I'm going to use, hopefully I'll have enough space here. I'm going to start by listing the nodes, x sub k or x sub I, whatever I was calling these in class. And I'm going to list them all twice. So I'm going to list x sub 0 twice, x sub 1 twice, and x sub 2, oh sorry, -6 twice. This is going to help us encode the derivative information into this table. Next, I'm going to write down the 0th divided differences, and those are just the function values at each point. So f of x sub 0, we just computed that, is 7. And I've repeated the node, so I'm going to write it down again. F at x sub 1 is -8. And again, I repeated the node, so I'll write it down again. And f at x sub 2 is 7. And I repeated it, so I write it down here. Then I go on to my next column, which is going to be the first divided differences. I'm just going to abbreviate it so I have enough room. And these are going to be, I'm going to use the pairs of divided differences in the previous column. So first I'm going to use these two values to make a divided difference. And these are using x0 and x0. So my first divided difference looks like x0, comma x0. And we saw in class that we're going to define this when we have a repeated node here. We're going to define this to be the derivative of our function at x sub 0, which we computed already is 8. Then I'm going to move down to the next pair. This pair has x0 and x1. My divided difference here is f with brackets, x0, x1. And this is the usual divided difference. So it's going to be x1 minus f x0 over x1 minus x0. So again, I take this term in the numerator, subtract this term, and then I subtract the nodes. So x1 minus x0. Just to save space, I'm going to replace each of these expressions with the value. So f of x1, the zeroth divided difference of x1, that is -8. And the first divided difference at x0 is 7. X sub 1 is -1, and x sub 0 is 2. I'm going to replace all that. And if you do this computation, you'll get 5. Okay. Now I'm going to move on to the next pair. Here I have x1 and x1. So the divided difference, x1 and x1. Again, this is a derivative. We defined it to be a derivative. So this is the derivative of f at x1, which we computed to be 2. I go down to the next pair. This is x1, x2, f x1, x2. This is going to be the 0th divided difference of x2 minus the 0th divided difference using x1, x2 minus x1. And again, I'm going to go ahead and replace these. So this term is the 7 here. Let's replace that with a 7. This term is this -8. I'm going to have minus -8, so plus 8. And then in the denominator, I have x2 minus x1, -6 minus -1, plus 1, and I'll end up with a -3. And then my last term in this column, I have x2, and that's again going to be a derivative term. It'll be the derivative of f evaluated at x2, which we computed earlier to be -8. Okay. I'm just trying to save space here. Make sure I get all of this. Make it a little smaller. Okay, so hopefully I can fit the rest of this in here. I'm going to go on to the next column. These are going to be the second divided differences. All right, now I'm going to proceed with the usual divided difference procedure. I'm not going to need to sort of define any more derivatives because I'm just going to use these values to construct the next column. So using these first two pairs, or this first pair, I've got this number and this number. This will be the divided difference of x0, x0, x1. So it's sort of like these two are going to match. So I just list it once, but I list the outside ones too. So I have x0, x0, x1. That's going to be equal to this term minus this term in the numerator. So really it's f x0, x1 minus f x0, x0 all over x1 minus x0. I want to point out that this first divided difference term in the numerator incorporates the last few terms in this expression. So you skip the first term, use the last ones, and then you subtract where you skip, you go the first couple terms and you skip this last one. So notice I have x0 here. Okay, and if I replace all these values, so I'm going to replace this divided difference with the value I computed. This one will become 5. And I'm going to replace this divided difference by this value that I computed. So 5 minus 8. Give myself a little more room here. And in the denominator, I'll have x1 minus x of 0. This will give me 1. I'm going to go ahead and move along to the next divided difference that I'll compute. I'm going to use this value and this value. So I'll have f divided difference. I'm going to use x0. The x1s are repeated there, and x1. So f x0, x1, x1. It's going to be 2 minus 5 divided by x1 minus x0. And I'll end up with 1 here as well. Okay. And then I'll go down and compute this next divided difference. I've got x1, x1, x1 repeated, so I just list that once, and x2. So f x1, x1, x2. That will be -3 minus 2 over x2 minus x1, -6 minus -1. That'll leave me with a 1. And then I have my last divided difference in this column is x1, x2, x2. Okay, and that's going to be -8 minus -3 minus -3 over x2 minus x1. And I'll end up with 1 there as well. Go to my next column for my third divided differences. All right, I'm going to go and take these two. I'm going to use x1, x0, x0, x1, and then you sort of like add on the last term. So maybe I shouldn't have said that they repeat, but it's like x0, x0, x1, and you add on the last term here. So I'm going to end up with x0, x0, x1, x1. It'll be 1 minus 1 divided by x1 minus x0. So I'm going to get 0 here. Maybe I should write it out because that's not always going to happen. It just happens in this case. So it just so happens that this is going to happen in this case. It's going to actually happen for the rest of this column. I'm going to get zeros. That's not a typical thing. It's just that for this example, this is happening. So don't like just assume things are 0. We're going to actually write down all the computations just so you see what's going on. All right, the next one is going to be x0, x1, x1, x2. x0, x1, x1, x2. Again, I'll have 1 minus 1 in the numerator because I have 1 minus 1 here. And then I'm going to subtract in the denominator x2 minus x0. That's going to give me 0. And then here I'll have x1, x1, x2, x2. x1, x1, x2, x2. And again, this is just happens to be what's going on in this problem, but I'll have 1 minus 1 in the numerator, and then x2 minus x1 in the denominator. So that gives me 0. Okay, I have 2 more columns to do. Let's see if I can make this a little bit smaller so I can fit everything in one go. I don't know if it's possible, but let's see if I can write small enough. So these would be the fourth divided differences. And you can see that these are going to be 0, but it's just because of this problem. I'm going to have 0 minus 0, I guess I should say this way, 0 minus 0 in the numerator there, and 0 minus 0 in the numerator here. But I'll write out what the expressions are going to look like anyway, just so you can see. So this next divided difference is going to be x0, x0, x1, x1, x2. x0, x0, x1, x1, x2. That's going to be 0 minus 0 over x2 minus x0. So I'll have 0 here. The next one is going to be x0, x1, 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 x2. x0, x1, x1, x2, x2. And again, I'll have 0 minus 0, 0. And my very last divided difference, again, I'm just writing this out so you can see all the steps, but I'm going to get zeros again. Oops. Let me not cross things out here on accident. Oof, okay, let's see if I can fit this here. Fifth divided difference. I'm combining these two divided differences. And when you get to the very last divided difference in your table, you're going to have, if you've done it correctly, you're going to have the divided difference where you include all the nodes. And if it's a Hermite polynomial, it's all the nodes listed twice, which is what you started out up here. Let's double check. We're going to have x0, x0, x1, x1, x2, and x2. So indeed, that is all the nodes listed twice. x0, x0, x1, x1. I'm running out of room. x2, x2. And then normally I would subtract this term minus this term, but they're both 0 in the numerator, so I'll have 0 here. Okay. But I wanted to write all of this out so you can see sort of how it builds on itself. Now, let's write out what our polynomial looks like after all this work. Let me get myself some more paper here. Okay, let's get some more room here. Okay. Now, H5, this 5th degree Hermite polynomial, what I did in this table was compute all of the coefficients for this polynomial. And the coefficients appear in the first row of each column. But even though the columns are sort of getting shorter, I'm going to take the first row of each of those columns. If you wanted to write this out using the notation we've been using in class, it would be the 0th divided difference of x of 0 plus the next term here is x0, comma x0 times x minus x0 plus the next term here is 0, 0, 1, the divided difference x0, x0, x1 times, and the linear factors, I mentioned this in class, but I'll say it here, the linear factors that you list contain the nodes in the previous divided difference. So in the previous term here, I had x0, x0, so I will have x minus x sub 0 times x minus x sub 0 plus my next term, my next coefficient here is this one. So divided difference x0, x0, x1, x1. And the linear factors include the nodes in the previous divided difference. So that gives me x minus x0, x minus x0 times x minus x1. My next term is this one over here. So I'll move to the next line. I have plus f divided difference x0, x0, x1, x1, x2. And the linear factors, again, are the ones that appear in the previous divided difference. So I have x0, x0, x1, x1, x minus x0, x minus x0, x minus x1, x minus x1. And the very last term I have here includes all the nodes listed twice because this is a Hermite polynomial. I have x0, x0, x1, x1, x2, x2, and all the nodes that were in the previous divided difference. So x minus x0, x minus x0, x minus x1, x minus x1, and x minus x2, and I stopped there. Okay. Now I need to sort of substitute all the values I have that I computed earlier. So I know that this term here is 7, this term here is 8, this term here is 1, and then all the rest of these are 0. So these are all going to go away. We'll end up with 7 plus 8 times x minus x sub 0 is 2. Okay, I'm plugging in x sub 0. Plus, this term here is 1 times x minus x sub 0. I'll just say this is x minus x 0 squared. Really, that's what it is. Oh, and I should replace x sub 0 with 2. All right, and then this term is 0, and so is this coefficient and this coefficient. So really, plus 0, plus 0, plus 0. Okay. And if you expand all of this out, you'll end up with x squared plus 4x minus 5. Okay, now, if you remember, this polynomial is actually the one we started with. So this was kind of a funny example, but I wanted to do it just to show you what's going on. Why is that? Because I had 3 points that I wanted this polynomial to interpolate. And there is the quadratic polynomial that goes through these points is unique. So I actually should expect to get that polynomial. That's not going to happen every time. It was just, a function of this example because I had 3 points and I was writing down a quadratic polynomial. Now notice that I asked for h5. And you would think this has a 5th degree polynomial, but it's degree at most 5. And notice that we just ended up with zeros for our other coefficients. That's because I'm just using 3 points and I am interpolating a quadratic polynomial, so I'll end up with a quadratic. I mostly just wanted to do this example to sort of show you the process for building the table. Don't expect to end up with what you started with all the time. This was just, a special example where that happened. I hope this helped clear up some of the divided difference stuff or Hermite polynomial stuff. If you were just constructing a divided difference, a Newton's divided difference formula or a Lagrange polynomial that just went through these points and you didn't have the derivative information, you would not repeat the nodes and you would just do a normal divided difference table. But because this is a Hermite polynomial, we have to include the derivative information, and that's why we repeated the nodes. All right, so I hope you found this video helpful, and let me know if you have any questions.